Okay. Yeah. Okay. Hello, and welcome to my presentation. My name is Katrin Ehrenmüller, and I'm presenting you work from our project called SENSE. We are working on cyber-physical systems, and we are looking into exploring how we can use LLMs in our use case. So cyber-physical systems in general are just smart systems with some physical parts that have more computational functionalities. In this use case, we are mostly working on smart grids as cyber-physical systems. So I first want to go into details on our use case. So here you have an example of a smart grid entity. So we have a garage with some electric vehicle chargers and a battery, and there are some sensors installed. So all the blue circles are sensors in our system. And here you can just basically measure what's happening. And then sometimes there is something happening in the system. So for example, here we have an overload at the garage that is collected by the sensor. And obviously we have some use case, stakeholders of the use case. So the facility operator in this case, so the guy operating the garage as a facility, and they want to know why did this overload happen. So ideally we get an answer that is something like there was a low battery state of charge, and that's why there was an overload, because the high charging couldn't be handled. So this is what we are working on to create as explanations in the SENSE project. And to create such explanation, we need causal knowledge in the system to answer these questions. So going into details more on the use case, we're having this, so the whole setup of this garage as the cyber-physical system setup, we have represented in a knowledge graph as part of the project. So just as a background knowledge, and we do have some causality already in the data with a very specific structure, because we need to use it for basic real-time explanations. We don't just need A causes B, but we need the type of causality. So we have it as whether A causes B or A enables B, which is sometimes just a causal relation all the time, but it does entail some different semantics. We need the temporal constraints, so whether A causes B is happening only if they happen at the same time, or if there is like some temporal lags, and then topological constraints in terms of how far A and B have to be in terms of physical proximity, basically. As an example, I have here high charging causes envelope violation. So basically, if there's a high charging at one of the chargers, this can cause an envelope violation at the garage level. So basically we have the type of causality, we have causes, then we have the overlapping as they have to be temporally overlapping. And then we have at parent platform, which means the high charge has to be within the platform where the envelope violation happens. Yes. So basically what we have in our project, we already define these causal relations with experts. So we have some ground truth data that we can work with for trying out to use LLMs to help experts in the process. So as I already kind of mentioned a bit, we have this traditional workflow of how to define causality in our cyber-physical systems. So usually you just have this setup of the system, so how everything is connected in a cyber-physical system, or in this case, a smart grid. And then we ask the expert to define some states that are interesting to them. For example, we have the overload, which is one of the states that could be interesting, and the low state of charge is another state. And we just collect basically stuff that is interesting to them. And then once we have these states, we are looking further into defining causal relations between the states. So for example, which one is the cause of the other one, to actually get to the causal model that we are interested in. So why is this not the ideal workflow? Causal discovery is super time-consuming and tedious, and also just expensive because experts are expensive to talk to. So our hypothesis is basically that LLMs can offer assistance in a more hybrid workflow, as we already had in these workshops, just LLM in the loop to assist humans in the process. So there is some research already that LLMs can help as kickstarters to learning causal inference, as we already also learned in this workshop. And there has also been some investigations on LLMs for causality acquisition with promising results. So what we did is basically we are defining for our use case a hybrid workflow where we just use the setup of the system plus some trigger state that the expert tells us they're interested in. And we put this, we ask the LLM to define system states in a first step. So basically here we have two prompts. The first one is just to input the data and make sure the LLM can rephrase and like actually explain what they are doing, what they understand about the data. In the second prompt, we then ask it to actually define the system states, which is then these generated cyber-physical system states. And they should be given back to the expert basically to validate them, to say, okay, these are system states that actually make sense. Once we have these validated states, we then go back to the LLM and ask the LLM to define causal relations between these states that have been defined and validated. So in the third prompt, we then look into, so given the following state types, which causal relations do you propose in terms of these cause-effect pairs, temporal, topological, as well as causal types. Yes, so then basically we have a generated causal model that should be validated by the expert again. So then we will get, in the end, a causal model that is validated by expert, but also helped by just not having the expert to do the whole process, and maybe even finding new variations that they might not have thought about. Yes, so how did we evaluate it? We have 3 different evaluations I want to go into. So basically, the first one is just looking at the full workflow as one. So we start with the setup, plus this trigger state, it's not in the picture. And then we just go through the whole process and evaluate the difference between the generated causal model and the causal model from the experts that we have from the ground truth data. So we evaluated everything with GPT-4o plus DeepSeek R1 as the state-of-the-art models. Yeah, and you can see, so we looked into precision and recall. Recall is not so great, which does make kind of sense because so we have one full workflow where we didn't really check too much on whether the generated system states and the original system states are the same. So basically, it was a bit hard to map what the models had as system states and what was proposed by the experts. But for precision, just the pairs between cause and effect were quite all right, but then going into details, the performance decreases quite a bit. So going into details on evaluation, we also just checked step 1. So basically now we just go to the generated system states and look into how they're close to the ground truth system states. So this one was a lot better. So you can see that it's just if you don't do the validation on the way, there can be some decreasing of the performance. Yeah, and then the last one is that we also just validated the last step. So we take the states from the ground truth and then just do step 2, basically. And here you can see that the recall is a lot better than before, as well as the precision being a bit better. Yeah, but also here we can see that there's a bit of a decrease going into details. Yes, so in the concluding remarks, I just want to mention that the cause-effect accuracy is quite high, with at least 67% precision, but we have decreasing performance going into details. In general, I think it's a super interesting direction to tackle this white sheet problem for experts. So not just thinking about making it like less work for the experts, but also just tackling this idea of having to start with nothing, but actually having something to, it's easier to say whether it's right or wrong than just having to come up with something. Yes, so limitations, we did not include observational data, but we already had a paper presentation that looked into that. But we also thought about including just causal falsification methods to basically have some loop to make sure this causal model is consistent with the data when we produce it. Yeah, so a very small advertisement from our side as well. We will be organizing the Centis workshop at Semantics in Vienna. So there is still paper submissions open if you want. Otherwise, I'm also happy to see some of you there if you're interested. And yeah, thank you for listening, and I'm happy to answer any questions.
Big question.
You said I have two questions. You said you didn't include observational data. So what did you give as an input? Was just the topology?
Yes, it was the sensors that we have and the devices that are in the system basically and how they are connected. And then we assumed that there is enough general knowledge from the LLMs to know how they are influencing each other.
And a very quick question for me. Maybe I missed out. You had a non-zero precision with the zero recall. What did I miss?
Yeah, so this one I didn't mention, but we did check so we checked recall in terms of what was in the ground truth data, but then we did ask the expert whether they found it as a reasonable basically possible state that wasn't actually used by the expert. And then there was the precision a bit higher than the recall. Yeah.
So the recall is in interruptible standard data.
But you should have, but I think you should have included those as the list of the valid ones because it doesn't, in my head, it doesn't make sense to have a zero recall and a non-zero precision.
Yeah.
I mean, you explain it, but then it would make sense that those that you found, which are relevant, they should be included in the ground truth, and then you have a recall of 30%.
Yeah.
I think that was a really good example of AI in the loop.
Yeah.
As we heard in the keynote today.
True. Yeah.
So in the interest of time, we'll move forward with the next presenter. And if you have any questions, Katrin will be here and we can always